Greetings and welcome to our lesson for equations and inequalities, specifically solving other types of equations. Here are the objectives for this lesson. We want to solve equations by factoring, solve rational equations, solve equations involving radicals, solve equations with rational exponents, and we want to learn to solve equations that are quadratic in form. You might have some experience with solving with factoring, but let's go through it. Procedure for solving equations by factoring, number one step, make one side equal to 0. You want to solve by factoring, so for example, we have x cubed plus 3x squared equals 4x plus 12. We want to make sure that this equals 0, so we're going to move the 4x and the 12 over to the left-hand side, just so we keep that x cubed positive. You don't have to, but it makes it a little bit easier when you keep the term with the largest power positive. Next, we're going to factor the left-hand side. We've got some strategies to be able to do this. Generally, we're looking for GCF, greatest common factor, first. Then we're going to see if we have something that we can utilize our factor arsenal of knowing to be able to factor it. So since this has 4 terms, I generally look at it to use factor by grouping. So I would group the first 2 terms and the last 2 terms on the left-hand side and see if there's any common factor I can pull out of there. And indeed, the first 2 terms factor as x squared times quantity x plus 3. And the second 2 terms, I can factor out that -4. And I get -4 times x plus 3. And as you see, they both have x plus 3 in common, so that's its GCF. We'll pull that out and put it all together. So x plus 3 times x squared minus 4. Step 3, we're going to use the zero factor property. Now, yes, you can factor if you want a little bit further. If you see that x squared minus 4 as something factorable, go for it. If you don't want to factor it, we do have that square root property to be able to solve after we break it up using the zero factor property. And that's what I'm going to do. So I'm going to leave it as x squared minus 4, but I'm going to set each term to 0. And then from there, solve for x. So here we have x equals -3 and x equals +2 and x equals -2. Step 4, you got to check your solutions. When we're working with these problems, there is a possibility that one of our answers, or even both of the answers, may be mathematically wonderful, but it may not fit the problem at hand. Additionally, by some of the techniques that we use, we can introduce solutions that don't fit the problem, depending on what procedure we use to solve the equation. So always check your solutions. So let's go ahead and throw in x equals -3 and see what we come out as. And I'll let you look at these steps, but ultimately, we get 0 equals 0, and therefore it checks out. It's a good solution. And I'll let you go through and check the other 2, the +2 and the -2, and indeed verify that those are also solutions. I'll let you do that on your own. In essence, plug those into the original equation, see if you get something like 0 equals 0 or 3 equals 3. See if you get a true statement. If you get a true statement, then those solutions of -2 and +2 are wonderful. You can verify that -2 and +2 are indeed solutions, so our solution set is -3, -2, +2. Let's take a look at another example. Let's solve this by factoring. X to the 4th equals 9x squared. There's a lot of things that we have at our disposal, but I really like solving this problem by setting it equal to 0 and then using our factor techniques that we've learned up to this point to try and solve this problem. All right, step 1, let's set it equal to 0. X to the 4th minus 9x squared equals 0. Look to see if there's any GCF that you can pull out of these two terms. And indeed, we do. We have x squared. Once we pull out x squared, that's x squared times x squared minus 9. Either you can set both of those up using the zero factor property, or if your gut instinct is go ahead and factor some more, you could get it down to x squared times x plus 3, x minus 3 equals 0. But you could have used that first step of, let's see if I can find my little highlighter here. You could break it apart to where x squared equals 0 and x squared minus 9 equals 0 and solve those two problems. Or if you feel, you know what, I want to factor some more, you can get it down to x squared times x plus 3 times x minus 3. And again, our next step is going to be zero factor property. We're going to set each of those terms to 0. And we get a solution of x equals 0, or x equals negative 3, or x equals positive 3. Step 4 is always to check your solutions. So as it turns out, all three solutions are good solutions. 0 to the 4th equals 9 times 0 squared. Well, 0 squared is 0. 0 times 9 is 0, so 0 equals 0. Negative 3 to the 4th, well, I know negative times negative times negative times negative is positive, so I've dealt with the sign. 3 times 3 is 9, times 3 is 27, times 3 is 81. Negative 3 squared is negative 3 times negative 3 is positive 9. Positive 9 times 9 is 81. So 81 equals 81. We're good there. And of course, doing the positive is going to be 81 equals 81. And that looks good too. So therefore, our full solution set is negative 3, 0, and positive 3. When we're dealing with rational equations, meaning we have fractions and additionally that x value is down in the denominator, there's a few extra steps that we're going to want to take. First of all, let's find the LCD of all of our denominators. Our denominators are 6, x, and x plus 1. And since 6 has nothing in common with x plus 1, that's a whole entire thing, and x plus 1 has nothing in common with an x, and I know you're probably saying, but they each have an x. No, x plus 1 is a whole entire thing. That is a rabbit. X is a bear. A rabbit and a bear are not the same thing. I know, silly analogy, but it's just like that. X plus 1 is a whole entire different beast than an x. Therefore, our LCD is going to be 6 times x plus 1. We are going to multiply each term by the LCD. Once we do that, so we're multiplying each side, in essence, each term by the LCD, we'll ultimately get rid of the rational portion of it, the fractional portion of it. Okay. I know it looks a little bit messy, but we really are canceling out quite a few things. So 6x times x plus 1 times 1/6 ends up with 6x times x plus 1 all over 6. The 6's will drop out. 6x times x plus 1 times 1 over x plus 1. The x plus 1's will drop out. And then on the right-hand side, we have 6x times x plus 1 times 1 over x. The x's will cancel out. So we don't have any more fractions. We're left with x times x plus 1 plus 6x equals 6 times x plus 1. Now we're going to do our math on it. We're going to distribute. We're going to add like terms to get it as simplified as possible. So once we get it as simplified as possible, we're going to move everything to the left-hand side. And now we're to a problem where we are going to factor it. We're down to x squared plus x minus 6 equals 0. That was all for step 1, just to get it equal to 0. But now we're not working with those rational portions. We're not working with fractions. We're working with whole numbers. Factoring it, we get x plus 3 and x minus 2. Using zero factor property, we're going to solve. But again, once we have our solutions and we get x equals -3 and x equals +2, we're going to check those solutions. We did some kind of hardcore math there, and we may have, 1, made an error, and 2, we may have brought in some answers that may not fit our problem, so we always want to check our solutions. Checking both of our possible solutions, they do both work. I'll let you do that verification off to the side. Throw -3 in the original equation, you'll see that works out. Throw +2 in the equation, see if that works out. I do want to give you a little bit of warning here though. I'm going to bounce over to the original equation here. And because we have x in the denominator, we do need to be very aware of what x is not allowed to be. X is not allowed to be, x should not equal 1. That's horrible writing, but x should not equal 1, and x should not equal, or -1, and x should not equal 0. If our solutions were either a -1 or a 0, we'd have to throw it out because we don't want the denominator to be 0. That's why we check our solutions. Not only are they our values that we don't want, our restrictions, and likewise is our solution a good solution. I do want to be aware for this next problem of what x is not allowed to be. What are our restrictions? Restrictions are those values of x that cause the denominator to be 0. So x minus 1, if x is 1, x minus 1, 1 minus 1 is 0. So x is not allowed to be 1. When x is -1, that middle term, x plus 1, if that's -1, -1 plus 1 is also 0. And if you put a +1 on the right-hand denominator will be 0, as well as a -1. So x is not allowed to be positive or -1. Keep that in the back of your mind, because if we get an answer that's either 1 or -1, we're going to have to throw it out. It's just not in our domain. First step, let's find the LCD. The LCD of all the denominators, x minus 1, x plus 1, and an x squared minus 1, x minus 1 times x plus 1 is x squared minus 1. So our LCD is x squared minus 1. I'm going to multiply the left-hand side by this x minus 1, x plus 1. And we're going to multiply the right-hand side by x squared, x minus 1, x plus 1. So imagine this is one big old long equation. Here we go. After we distribute, there is a lot of cancellation, which is great. We end up with a very, or a less complex problem. That was our goal, get rid of the complexity. For the first term, this x minus 1 and this x minus 1 will cancel out, leaving us x times x plus 1. For the second term, the x plus 1 and the x plus 1 in the denominator will also cancel out, leaving us 1 times x minus 1, keeping in mind we have a subtraction there. For the right-hand side, because the x minus 1, x plus 1 does multiply to x squared minus 1, this x squared minus 1 will cancel the denominator out and leaving us 2x. So this is definitely less complex. X squared plus 1 times x minus x minus 1, all equals 2x. We're just going to distribute, add like terms, and now we're down to, and move everything over to the left, we're down to x squared minus 2x plus 1 equals 0. Now step 3, let's factor it. We get x minus 1 times x minus 1 equals 0. Of course, x minus 1 equals 0, and that way x equals 1. But remember what we said in the very beginning, where we don't want x to be 1. Mathematically, it's a great answer. It's a wonderful answer, x minus 1. We did all of our steps and we got us an answer, x equals 1. But it's not our solution because our domain does not include this value. It is what's called an erroneous solution. And if you throw it in there, you're going to get a denominator of 0, and that's undefined. And therefore, the real solution is the empty set. There is no solution to this problem, at least not in the real numbers. Okay, enough of those rational equations. Let's move on to radical equations. Now, I want to stress, in the previous example, we did throw in our value our answer that we got mathematically, and because it wasn't in the domain, we had to throw it out. The procedure that we're going to use to solve equations with radicals, generally speaking, at least most of the time, it will introduce an erroneous solution, and therefore you always have to check the answers to see if indeed it is a solution to the problem. It's just part of the procedure of what we're going to do can introduce erroneous answers. I'm not even going to call them solutions. They're erroneous answers. When it does become a solution, we get to keep it, but erroneous answers we have to throw out. Here's our problem. X equals the square root of 6x minus x cubed. Ultimately, I need to get rid of this radical. And to do that, I square the right-hand side. But if I square the right-hand side, I have to also square the left-hand side. Now, the problem becomes, so here we go. We're going to raise each side. We're going to square each side. We get x squared equals the square of radical 6x minus x cubed. This square cancels out this radical, and I'm left with 6x minus x cubed. Now I am going to go ahead and from here proceed like normal. I'm going to move everything to the left-hand side and set it equal to 0. And I'm going to factor my equation. I get x times x squared plus x minus 6, and it looks like x squared plus x minus 6 is also factorable. And therefore, I get x times x plus 3 times x minus 2 equals 0. Fair warning. This process of squaring, of blowing up your problem, can introduce erroneous solutions when you are blowing it up by an even root. So we've made it to the power of 2. 2 is even, and therefore this blowing up can introduce erroneous solutions. So it is a warning. If we were raising this to the cube, we actually wouldn't have to worry about it, surprisingly enough. But if we're raising it to 2 power, 4 power, 6 power, that even power can introduce erroneous solutions, aka what I like to call erroneous answers, because they're not our solutions, and we always have to double check. All right, so here's our possible solutions: 0, -3, and 2. Let's check them. All right, throwing in a -3, we get -3. Does that equal the square root of 6 times -3 minus -3 cubed? -3 cubed is -27, but a negative or a minus negative is a positive. -18 plus 27, which is 9, and the square root of 9 is +3. -3 does not equal +3. There's an erroneous solution. So x equals -3 is not it. Let's throw in our 2. 2, does that equal the square root of 6 times 2, which is 12, minus 2 cubed, which is 8. 16 minus 8 is 8, and that's not right. 12 minus 8 is 4, and the square root of 4 is 2. Okay, x equals 2 is a good solution. And let's try 0. Well, 0, does that equal the square root of 6 times 0 minus 0 cubed? Everything underneath the square root is 0. The square root of 0 is 0, and 0 equals 0. So -3 is extraneous, but 0 and 2 are good solutions, so our solution set is 0 and 2. When we have equations involving radicals, well, let me take a step back. When we had equations with rational, meaning fractions, we got rid of those fractions first, and then we carried on through our problem. With radicals, we are going to eliminate the radicals. Like in this case, we're going to square it. But the first thing we want to do is isolate that radical. We want the radical on one side of the equation and everything else on the other side of the equation. Right now, we have this plus 1. We're going to get rid of this plus 1 by subtracting 1 from both sides so it moves over to the right-hand side. Then we're going to go through our procedure of blowing it up, working through it, and checking our possible solutions. Okay, isolate the radical. We've moved that 1 over to the right-hand side, and now we're going to square both sides of the equation. This squaring, the purpose of it is to get rid of this radical. Squaring here is just because what I do to one side of the equation, I must do it to the other side. Now we have 2x plus 1 on the left-hand side and x squared minus 2x plus 1 on the right-hand side. Now, I don't care which side you move things to. I actually prefer to keep my largest power of x to be positive, but you can move everything to the left or the right. Doesn't matter. But ultimately, we end up with x squared minus 4x equals 0. Let's factor it. We get x times x minus 4 equals 0. Using the zero factor property, we're going to break it apart and solve. And we get x could be 0 or x could be 4. Remember, because we blew it up by a power of 2, we may have introduced an erroneous solution, and therefore we've got to check these solutions. It's not good enough to hit this part and say, yeah, my math was good enough. You've got to check them. All right, throwing in a 0, we get 2 times 0 plus 1. Plus 1, does that equal 0? Well, 2 times 0 is 0, plus 1 is 1. The square root of 1 is 1. 1 plus 1 is 2. And 2 never equals 0. Well, in our numbers, it doesn't equal 0. And if we throw a 4 in there, 2 times 4 is 8. 8 plus 1 is 9. Square root of 9 is 3. And 3 plus 1 is 4. 4 does equal 4. So our only solution is x equals 4. On occasion, your equation will have two radicals. Now, in the previous problem, we needed to isolate our radical. We should isolate our radical here. We need one radical on one side, one radical on the other side. But generally speaking, when we have two radicals and there's some numbers floating around, we're probably going to have to do this procedure not once but twice by blowing it up twice. All right, so let's isolate one of our radicals. So we get the square root of 2x minus 1 equals 1 plus the square root of x minus 1. At this point, we're going to square each side. Remember, it's the side, not just the radical. Once we square both sides, we end up with 2x minus 1 equals 1 plus 2 times the square root of x minus 1 plus x minus 1. Now you see, we blew it up once, and we did get rid of one of the radicals, but we didn't get rid of all of them. So now what we're going to do is move everything that we can and isolate this particular radical. Once we do that, we end up with x minus 1 equals 2 times x square root of x minus 1. Square both sides. Now you could have even divided it by 2, but then we would be working with fractions, so I don't mind having a value outside of the radical to square it. But you do have to remember you are squaring this value as well. So ultimately we get x squared minus 2x plus 1 equals 4 times x minus 1. We're going to set this equal to 0 and factor and get possible solutions to our problems. X squared minus 6x plus 5 equals 0. Factoring, we get x minus 5 times x minus 1. So our possible solutions, positive 5 and positive 1. But again, we blew this up and it was a power of 2. Not only did we blow it up once, we blew it up twice. So we definitely have to check our solutions. Once we check our solutions, throw in a 5, we get actually 1 equals 1. That's a good answer. Throwing in the 1, checking our solution, we get 1 equals 1. So in fact, even though we blew it up twice, both of our solutions are good solutions. So our solution set, 1 and 5. Let's quickly go over the steps that we did to solve equations containing square roots. The first thing we did was we isolated one of the radicals to one side of the equation and everything else to the other side of the equation. Now we squared both sides of the equation and we simplified it. If we don't have any radicals, we can continue. If we do have radicals, if we're still left with square roots, we have to repeat step 1 and step 2. Once we have our system, once we have our equation has no more radicals, we're going to solve the leftover equation. We're going to move everything to one side, set it equal to 0, and use our skills that we have of factoring to be able, or our quadratic equation, to be able to solve for possible solutions. Once we have possible solutions, we're going to check our solutions against the original problem, being very careful about our domain as well. Now this is going to make more sense than when you see an example, but ultimately we want to be able to solve equations in the form of u to some power that is a fraction m over n, and we want to end with a fraction with a power of k. So we're going to let m and n be positive integers and k is greater than 0. Some real number greater than 0. So m over n is in the lowest terms if m is odd, when we raise u to this power, it equals k, and therefore u will equal k to the reciprocal power of n over m. Okay, u to the mn, m over n, when that equals k, u will equal k to the reciprocal power if m is odd. If m is even, then u to the m over n equals k, and u would be plus or minus k to the reciprocal power. When it's odd, you don't need the plus or minus. When it's even, when m is even, you do need the plus and minus. Now here's the reason. On the k side, the m is in the denominator, and that means what root it is. So when m is odd, we don't ever worry about plus or minus, but when m is even, we have to deal with the plus or minus. So let's look at an equation that has this setup. X to the 3/5 equals 8. Another problem we're going to do is 2 times 2x minus 1 to the 3/2 minus 30 equals 24. And the third problem we're going to look at is 3x minus 1 to the 2/3 power equals 4. Now remember, we get to use this property about being able to flip the power, and if it's that even root in the denominator, we have to do plus or minus. All right, let's look at A. X to the 3/5 equals 8. This turns out to be x equals 8 to the 5/3. 3 is odd, so I don't have to worry about the plus or minus. But if I take the cube root of 8 is 2, and then I raise 2 to the 5th power, I get x equals 32. Okay, I took the root first. Sometimes for me, taking the root is easier. 8 to the cube root is 2, and then I raise it to the 5th power. That's 2 to the 5th, which is 32. And if you throw it in there and check it, it does. It is a good solution. Now let's look at B. b is pretty messy, so the first thing I want to do is I want to get that thing with the power over to the other side. All right, I can even get rid of this 2 by dividing by 2 from each side. That at least makes it a little bit easier to work with. And I'm left with 2x minus 1 equals 27. Now we're going to do that flip of a power. 3 is now in the denominator. 3 is odd, so I don't have to worry about plus and minus. But the cube root of 27 is 3. 3 squared is 9. So ultimately, I'm going to get 2x minus 1 equals 9. And from here on out, it's a problem we can solve fairly easily. We're going to add 1 to each side and then divide by 2, and we get x equals 5. And let's go ahead and check that and see if it works out. And indeed, when x is 5, we get 24 equals 24. I'll let you go through that at your own speed. C, 3x minus 1 to the 2/3 power equals 4. Now, when I flip over that fraction, I get 3 over 2. 2 is an even number. I am going to have that plus and minus. Plus and minus is added. Now, 4 to the square root is 2. 2 cubed is 8. So this is going to end up at plus or minus 8. All right. And ultimately, we're going to get possible answer of 3 or a possible answer of -7/3. We want to plug these in and make sure that these answers work. I'm going to let you work on verifying that these are indeed the solution set, but yes, they are -7/3 and 3. It just dawned on me that probably after this lecture, you're probably going to think, oh, the good old days where we just had x squared minus 5x plus 10 equals 0. Yes, we're getting into more complicated math. But if you think about our old quadratic form, which was ax squared plus bx plus c equals 0, and we didn't want a to be 0, otherwise we wouldn't have that squared term. Now we're going to replace that x squared and the x in the linear term with an actual expression that contains x, something like x plus 1. So we would have something like a times x plus 1 squared plus b times x plus 1 plus c equals 0. We're just replacing that expression with a u, and it will be in this form, quadratic in form, au squared plus bu plus c equals 0. Very similar, but now we have an expression with the variable x and not just an x. We're still going to use everything we know about factoring and our quadratic formula to be able to solve for the x value. But we have to be careful on what we're solving for. Or did we solve for u and then have to go back and solve for x? Or did we think we solved for x and skipped over the u part? And it will make more sense once we hit an example. All right, here we go. Let's look at this equation. It is in quadratic form. So we have x to the 2/3 minus 5x to the 1/3 plus 6 equals 0. Now what I'm going to do is I'm going to replace that x to the 2/3 with a u squared. And I'm going to replace the x to the 1/3 with a u because I'm going to say u equals x to the 1/3. I'm going to do a little bit of substitution here. If I let this u equal x to the 1/3, this becomes a u, and this becomes a u squared. And I can rewrite the equation. Instead of x to the 2/3 minus 5x to the 1/3 plus 6 equals 0, it becomes u squared minus 5u plus 6, which looks really familiar, or at least it should. Now I can factor it, solve for u, but then I don't stop there. I have to replace what u is originally. So it's a little extra step. U equals 2 or u equals 3. But what was u originally? u is x to the 1/3. So I have to put x to the 1/3 where u is. So we get x to the 1/3 equals 2, or x to the 1/3 equals 3, meaning x is 2 cubed, or 8, x is 3 cubed, or 27. Okay, so we're substituting u to stand in for something that's a little bit more complex. We're solving for u, but then we have to plug in what u was originally and solve that equation. And check your answers, and indeed our solution set is 8 and 27. Let's take a look at another example that I think that this u substitution technique will really help us. This problem looks extremely scary. X plus 1 over x all squared minus 6 times this x plus x over 1 plus 8 equals 0. But as it turns out, this x plus 1 over x is being squared. And this x plus 1 over x, if I replace this x plus 1 over x with a u, it will look like u squared minus 6u plus 8, which is completely more manageable. So let's go ahead and do that. Let's substitute u in where we see x plus 1 over x. And we get a simplified version where we have u squared minus 6u plus 8. Now we can factor it and solve for u. So we have u could equal 2 or u could equal 4. But we didn't start our problem off with u's, we started it off with x's. So we need to replace what u is with x plus 1 over x. So x plus 1 over x equals 2. I'm going to multiply everything by x so I can get rid of that x in the denominator. I get x squared plus 1 equals 2x. Moving the 2x to the left-hand side, I get x squared minus 2x plus 1 equals 0. Factoring. Now I'm going to take the square root of both sides, and because it's a even root, I do have to do plus or minus. Ultimately, it won't make a difference because it's square root of 0. But it is part of the process, and I get x equals 1, at least possibly equals 1. And it turns out that you throw a 1 in here, 1 plus 1 over 1, so 1 plus 1 is 2, that checks out. Now let's throw in that x plus 1 over x equals 4. Again, same procedure. I'm going to get rid of that denominator by multiplying by x. Ax squared plus 1 equals 4x. X squared minus 4x plus 1 equals 0. And because this is not factorable, we'll use the quadratic equation, and we get x equals 4 plus or minus the square root of 12 all over 2. And it turns out that both of these equations, both of these possible solutions are indeed solutions. Yes, you would have to throw it in. You would have 2 plus the square root of 3 all over 1 over 2 plus the square root of 3. That turns out to be 4, and the minus also turns out to be 4. So we have three solutions to this problem. Let's tackle a very interesting problem. Your sister's 5 years older than you are. She decides she's had enough of Earth and needs a vacation. She takes a trip to Omega 1 star system. Her trip to Omega 1 and back in a spacecraft traveling at the average speed v took 15 years, according to the clock and calendar on the spacecraft. But on landing back to Earth, she discovers that her voyage took 25 years according to the time on Earth. So according to her, in the spacecraft, it only took 15 years, but in Earth time, it took 25 years. This means although you were 5 years younger than your sister before her vacation, you are now 5 years older than her after her vacation. We're going to use this special formula to calculate the speed of the aircraft. So t naught equals t times the square root of 1 minus v squared over c squared, where t is the observed time in the fixed frame of reference, v is the speed of the moving of the reference, meaning the spacecraft speed, and c is the speed of light. Now, when we substitute in our starting time, 15 years is our t naught, 25 years, our Earth time, is our t, which is our fixed time frame, we get 15 equals 25 times square root of 1 minus v squared over c squared. Moving that 25 over to the other side and reducing that fraction, we get 3/5 equals square root of 1 minus v squared all over c squared. Now here we go. I just took the square root I squared both sides. I blew it up and took square of 3/5, which is 3 times 3 is 9, 5 times 5 is 25. We get 9/25. And taking square of a square root gets rid of that square root. Ultimately, I'm trying to solve for v. Okay, moving the 1 over. Aha! We can take the square off of both of these guys. Now I'm going to take the square root. And because I took the square root, I have to say plus or minus on the right. So v over c equals plus and minus 4/5. Now, multiplying both sides by c, because this is speed, I really don't care about the negative 4/5. I'm really only worried about the positive 4/5. So our v, our velocity of the spacecraft, is 4/5 c. And if we get a decimal, that's 0.8 c. The cool part about that is if I change that 0.8 to a percent, we know the spacecraft is traveling at 80% of the speed of light. Now, the cool part about this is if you throw it into a calculator, we actually get how fast the spaceship is traveling. Now, I'm going to just round this. That's about 240 million meters per second. Or, for us in America, that is about 540 million miles per hour. That's really fast. Alrighty, we've reached the end of this lecture. I know it was a lot. I mean, we did things with rational equations, radical equations, powers that weren't just whole numbers. They were fractional components. So we did a lot today. So until next time, be seeing you.